You can go ahead.
Can you view my screen, Ramesh?
Yes, yes.
Okay.
Thank you.
Yeah, you're good to go.
Okay. Today's session, we have our case studies. Now, in the case studies, which is in the first 20 odd minutes, we have some of you who have solved that little puzzle which we had shared in the group. And from Tenmuri, there is a fairly long case study. So we want to really spend a lot of time on Tenmuris. And the puzzle per se, honestly, it was more for us to sort of connect algebra, geometry, and not see any of these things as silos. Um, well, at some level, we can say algebra and geometry should be connected. At a slightly larger level, we should be thinking that all of mathematics is quite connected. And at an even larger level, we should think of all sciences and math being connected. And even at a larger level, learning generally is connected. So even if you don't go up to that level of abstraction and say that all learning is somewhat connected in some way or the other, we never know what we learn in which subject and what it spills into. We could definitely say that algebra and geometry are quite connected. And not just they are connected, more importantly, we can do good algebra if we understand good geometry, and we can do good geometry if we understand algebra. And they very, very directly get connected in calculus in any case. And that puzzle was really more on something like that. And some of you got the right answer. Wonderful, Sushma, Rekha, as well as Ganapati. And what we could do is we could go straight into, and we had a few other questions in terms of, the combinatorial problems or the heuristic problems, which Bama was talking about, like Königsberg and map coloring problem. Can we think or come up with any other problems or any number of problems like that? We didn't get much of a response. I'm going to put it down to saying that we had only a 1 week gap between the last one and this one. Let's then move into Tenmuris and spend some time there. Tenmuri, all yours.
Hi all. Yeah, I attended last week's presentation by Ramesh and Bama. Yeah, so there was a request to submit a real life scenario where we use algebra as well as as a simple single variable or a two variable problem, and also how we can bring in simultaneous equations into our real life situations that we see. So one of the places where I see algebra can play a role itself is in recipes or in cooking. Like we all take to looking on YouTube for recipes in which they mention about how to make a certain dish, and then very neatly at the end of it they will say this is how many laddus you will get or how many cakes you can bake with this recipe, and it can be changed according to the number you want to make. So that's exactly the application where we can use algebra. The outcome or the number of laddus or cakes we want is the variable, and based on that we need to increase or decrease the ingredients. And secondly is also the time to prepare. That is also nowadays given very neatly in the recipes. What is the prep time and then what is the actual cooking time. And if we are going to take this outcome of the our cooking to a sale, then we have to put a price to that. What is the cost for preparation, and then what is the price we want to sell. So all of these actually can be modeled either as constants or variables. And so I just put a simple scenario here. Sunil is a home baker and he prepares cakes for orders which he gets online or through his friends. And then the scenario goes like he also goes into a contest where they give a specific time in which he has to bake certain cake, and also make a fixed amount so that he can get a price for the cake that is being baked. So the first one where we want to just indicate a single variable equation is like the time required for preparing a cake. Simply, if you say that equation here, we have t equal to 30 plus 15. In any baking recipe, we'll say that first we have to preheat the oven, and then the recipe itself says that the baking time will be 30 minutes at this temperature, but maybe the temperature we can keep it aside as a prerequisite. So a single variable equation can be modeled as time t equal to 30 plus 15, where the value is amounting to 45 minutes for baking a cake. And another one also could be the price that you would want to quote for a certain weight of a cake. This also, like when we go to a bakery for to order a birthday cake or a celebration cake, first they will ask how many kgs you want. The price goes by the kg of the weight of the cake. So the price can be modeled as 40. Here I'm saying for 1 kg of a cake, the price is 450 rupees. And then additional costs like either packaging or if it is on delivery, then additional costs will come. So typically prices will be modeled with the weight as well as with the other costs. So these are simple single variable equations which can come in the baking scenario. Can we go into the next slide? Yeah. Secondly, when we want to bring in more variables, like, you want to find the cost based on the weight. So there I have fixed the previously price equal to 450 plus 125 means there the kg is 1 kg. But suppose you are going for a wedding, then the number of guests are going to be more. So we are going to order more kgs of cake. So the baker is going to ask how many kgs you want. That's so I have modeled the next equation as C equal to W into 450 plus 150. The W is the weight in kgs for the cake and 450 is the nominal for per kg. So here we have the cost, which is equal to W into 450 plus 150, which is a constant. So these are quite simple. Next is suppose we want to see wherein a quadratic equation can be used in such a scenario is you are having a square cake, and you typically a lot of decoration goes on the top of the cake. You make an icing and then a figure is drawn, especially if it is children, they want either Spider-Man or their favorite cartoon to be drawn on that. So typically a lot of work goes on the top layer of the cake. And this itself, the person can actually charge based on the size of the cake. The baker is going to say, okay, this cake is a square cake, which is having a side of say X. Then the whole area is going to be X squared. And he will keep something like this in his mind. He will not be actually doing the calculation. He knows that if it is going to be a 30 centimeter cake, I will need so much of icing and this many amount of decoration and like that. So there can be a simple quadratic equation. Here actually the text has not come out properly. Here the area will be X squared, not X2. And so the cost for the decoration itself, which is D, is equal to X squared by 4 plus 50. So he basically keeps something like this in his mind. Sunil, while saying somebody comes and asks, I want to make a good decoration, then it will be, okay, this is the area of the top layer. I'm going to charge you additionally X squared by 4 plus 50. So if 30 centimeters is the side of the cake, the decoration cost is going to be 900 by 4 plus 50, that many rupees. So this is quite simple. Likewise, we may have for other rectangular or other
Where did
shapes
that
of.
by 4 plus 50 come? I didn't catch that very well.
That is just my own interpretation, because like you don't have to. I mean, 900 seems like a large amount for a cake. So these are just my values. It is nothing to do with the
Got it.
equation itself. Yeah. So it's basically based on the area, you divide by 4 and then add some constant, like maybe a service or a constant value to that to charge for the decoration of the upper layer. And then going into how basically simultaneous equation comes here again, like we have to have certain constraints during baking. Like we do have baking contests, or even when you are having during Christmas or certain times, these home bakers, they get a lot of demands, so they are also short of time. So here I am trying to model a constraint with time, and then the amount that can be earned by the baker. So somebody comes and orders a set of cupcakes plus X amount of pound cakes. Pound cakes is typically the rectangle or the square simple cake. And during previous calibration, say Sunil the baker has already found out that for one cupcake, I will need about 1 minute. And for baking one 500 grams of pound cake or 1 kg of pound cake, that unit doesn't matter. I need 25 minutes. So, and then the next constraint he is putting on himself is, I want to at least earn like 1,000 rupees. Suppose I'm putting an effort for 1.5 hours. That order itself should fetch me at least 1,000 rupees. So for this, we are attaching a price for each cupcake. Say one cupcake will be 20 rupees. That's the last but one line. And then one piece of the pound cake is going to cost 100 rupees. So two constraints are there here. The baking time is a constraint. And secondly, the other one is how much of money the baker can earn in that given time. So can we go to the next slide, please? Yeah. So here we are saying 1 minute is the time. X is the number of cupcakes that he can bake, and Y is the number of units of pound cake that he can bake. And the previous calibration, he's just saying that for one cupcake, it will be 1 minute. But typically, they won't put one cupcake. It will be a tray of 16 or 20 or 12. So here I'm just giving it as per cupcake. So it is 1 minute per cupcake plus 25 minutes for a pound cake. Totally, he has only 150 minutes. In this is the time constraint. The second one is the money that can be, that it will fetch, or for how much he can sell it. So one cupcake is 20 rupees, and the one unit of the pound cake will be 100 rupees. And here he wants to at least make 1,000 rupees, putting an effort of for 150 minutes. So these are like some constraints that bakers and even people working in the confectionery business will have. And this can be easily solved because it is a simple and simultaneous equation from which we get he can make about 25 cupcakes and 5 units of the pound cake if he wants to satisfy both of these both of these constraints given to him. Okay. So this is some scenario which I thought with the baking real life like events.
Very nice.
And regarding the second one, I couldn't put much time. Third one, of course, it was my solution was also similar to what Ramesh had put. We basically use the tangents as well as the to find out the area of the triangle.
Yeah. If I can ask this one thing to everyone, how many of you attempted solving this, and what did it do to you when you were solving it? If I can ask, any of the people who tried solving it, why don't I go with, say, somebody like Sushma and Rekha and Ganapati, the 3 people who did solve and post their answers as well if they are there. But anybody else can come in also. Did any of you, if you tried it, and what did it do to you?
Good evening, sir.
Yes, Ganapati.
Sir, first of all, I was thought that what type of triangle it is. Is it a triangle? Because we had actually the shading part removed from the geometrical. I thought of removing some shading part and others, but I couldn't get it. Then I start assuming, oh, it might be it might later. Sometime we go with assumptions, okay, construction or something like that. Then I started. Let it be a right angle triangle. That I thought that blue color is in perpendicular for the base. Then I started using, okay, this is let R be, or whatever the measurement is, a radius. Another, I assumed it as something, some variable there. Then I started using Pythagoras theorem. Somewhere I got the link there. Without right angle triangle, definitely I did not had any idea of that particular, only with the circles how to solve. Once right angle triangle, when I assumed it, I was able to relate, okay, I can solve it. Without right angle triangle, I did not had an idea that we can solve until you post it. Once if you post, then I came to know, okay, this is how we can solve that.
But yeah, great. But what did you feel when you were doing it?
So it is a challenging one, sir. It's not so right. Generally, how we go with the geometrical questions, it's not that easy to go with it. And I also searched in the Google how to solve. I cropped this image and gave for Google scan to curious to know the answer, how to solve this puzzle. They have different types of same type of images, but not this particular. I couldn't find in Google lens to scan that particular. I couldn't get it. Then scratch. Then when I assumed it as a perpendicular, I was able to solve it. Till that, no idea whether I was able to get it or not. I did not had any idea to solve it.
Let me ask you a follow-up question. So let's say I posted this puzzle with a deadline saying that, please post your answers within 3 hours. And then after that, I will publish the result. How would you have felt if you hadn't had a chance to solve it properly?
Sir, it was really challenging, sir. My 17 years of teaching mathematics and physics.
No. I'm not asking that, Ganapati. So my idea is not whether it was a good puzzle. It is like you went through a certain emotion when you solved it. Imagine if you had posted the puzzle and said, we will give it 3 hours and then post the answer. You went through a struggle. I would have released you of that struggle, right? In 3
Yes,
hours,
sir.
I've given you the answer. Would you have felt good or not so good about it?
Sir, definitely, sir. Definitely, it was.
If I posted it along with the answer, would you have felt good about it?
No, sir. It was okay. I was just used to read it. Okay, like a newspaper. Okay, so this is a logic. I used to get it. It was not so challenging, and it was a brainstorming for me also, sir. It was I was able to think how to solve with respect to the area, sector. I started using all geometrical part, because the area has to be identified. Okay, area of a bigger circle plus area of a smaller circle. Okay, that is an two lines which comes with an arc. How to find it? I couldn't get the formula there. Many errors. Brain starts thinking. Once the answer is there, definitely it's nothing. The brain will not work. It's just reading. If answers are not there, it really works.
Yeah.
Runs everywhere. 360-degree, the brain starts working.
Yeah. Because that's something we have to deeply reflect on. Anybody else who tried, and what did you feel? Okay. Because the one thing we need to kind of reflect on here, it's okay. I mean, there is a problem. We have a solution. We put some triangle and some tangent and this and that and rearrange some terms and got some answer of 21. Forget all that. The main thing is it does something to us when we solve something like that. There is a certain kind of joy in the pain. Okay, because if the problem was very easy, we wouldn't have found the same amount of joy. And we'll normally think of joy and pain as opposite sides. Here, it's one of those peculiar things. The more the struggle is, the more the joy is in good puzzles. Okay, because normally we'll say that if something is painful, it cannot be joyous. If something is joyous, it cannot be painful. Here is one of those things where there is a struggle. There's a certain kind of enjoyable pain that happens. in the struggle, and then comes the solution, and the solution has a great amount of satisfaction. And all of these words, if you see, pain and joy and satisfaction, are all emotional words, nothing to do with mathematics at all. This was one of the things we were putting to as a thing last week as well, saying as much as possible we should be able to create and make mathematics quite emotional in a class, where there is a certain joy and pain and struggle and euphoria and satisfaction and fulfillment. If all of those elements come into a math class, then it becomes a lot more joyous. This was just one little problem. If you folks want more of such things, I can keep posting it. There is, because I'm not creating any of these things. I can tell you there is a lady called Catriona Ang or Ann or something like that. She's on Twitter and she posts all these beautiful puzzles. And she has got such a cult following. She's a teacher and she has a super cult following. I'm one of the followers of this lady. Catriona Ag or something like that is her name. Bama is another follower of this lady. So all of us, all the sketches are so beautiful. It's like this only. It's very human. All our sketches also very nicely done. Okay, wonderful. So we can press on, Nadia. We can go into yeah, this is all Sushma, if you're there, but we have already talked about the puzzles. Sushma, Rekha, and Ganapati has talked about it. Yeah, we can move forward to Sendil section, Nadia.
Yeah, for me also, I'll just talk about the puzzle a little bit. So
yes, please.
I couldn't really solve it, but it was extremely restless for me that night. And I woke up in the middle of the night also and staring at that phone, and it was, and Nila was next to me, and then she was also looking at the puzzle, and then like she was asking like, how do you solve such silly parameters they have given, and with these things you can't even do anything. She was like immediately giving up. And I kept just staring at this for a while, rotating the phone on different sides, and then like it was just no, I think that restlessness itself is quite important for children to feel in the class. But yeah, we have to hold it tight so that it's a thin line between giving up and enjoying that restlessness. So yeah, need to hang children around that space. Yeah.
Ramesh sir, is it possible to share the solution of that puzzle in the group? Is it possible?
I think I put it there. All of us have, many of us have solved it. One of the solutions, I think the way I tried to solve it, I posted it there also.
Yeah.
Okay.
I can repost it, Dhanashree.
Yeah, okay. Thank you so much. Actually, I'm a bit late, so I've missed, I think. Fine, thank you.
Yeah. The solution itself is, of course, we can post the solution, no issues at all. The idea is something we keep coming back on this Reimagine Math program, that ultimately we have to all deeply understand that an answer to anything, right, will stop thinking. Any answer stops thinking.
Yeah.
Remember this. Any answer stops thinking. And therefore, if you want a thinking classroom, the one thing you should not have is too many answers to too many things. And just allow it to simmer there, allow it to breathe, allow it to rest, allow it to create unrest, allow it to create emotions, all of that. Do not answer it too early and say, this is what it is. Let me tell you what is arithmetic progression is not the way we want to go. Let me tell you what is simultaneous equation is not the way we want to go, because we kill it, because the answer comes and kills it. Now the child will know the procedure. We have basically converted the mind into an automatable thing. It just becomes a small factory by itself. Now, any simultaneous equation, you send it to the mind, it will produce an output of what is X and what is Y. The mind has become a factory. So we have to allow the mind to be a mind, and factories have to do the job of a factory, not the other way around. That's all the take home we need to keep coming back to in Reimagine Math, because we do not want to answer anything with a child. That doesn't mean the child will not be able to find the answer. Don't get it wrong. The child will find the answer for everything. We don't want to preempt and abort the process of thinking itself, because the process of thinking will lead to the answer. Of course, I'll post the answer, Dhanashree, but the answer itself is not so relevant. Whether we got 21 or 18 or 15 doesn't matter. 21 probably is the right answer because many of us got it.
Okay.
In a world where majority wins, then that is the right answer. Yeah.
Fine, Ramesh. Thank you.
Yeah, and as you said, it's more important for the question to be living in us. I think that is more important, and I also feel sometimes it's worth to make a lot of mistakes and struggle in spots until we find the answer.
Correct.
Yeah.
Correct.
Okay, sure. With the arithmetic and geometric progressions today, this arithmetic progression is in some curriculums it's available, in some curriculums it's not available. But I always felt arithmetic progression is always there. In NIOS, I've seen this, but IGCSE alone, I haven't seen this. But I see this in CBSE also. So, but this arithmetic progression, though it comes in 10th standard or 9th standard formally, arithmetic progression or arithmetic growth is something which we have been seeing right from grade 2 onwards, like where you ask about what's the next number in this sequence, like what comes in these things. And so that is always there. So children can find what is the next step, and by looking at it's like arithmetic growth, we can see it as adding the same amount over and over again. And it's one very simple example is like climbing the stairs, where every step is of the same size and you climb one step at a time or 2 steps at a time. But for every jump, you take 2 steps above and then you keep moving forward. So that is a simple example for arithmetic progression, where wherever if we start at say 6 and we keep adding 2 each time, then it moves like 6, 8, 10, 12. It's about two words, keywords would be like steady, consistent increase or decrease. Steady and consistent is the keyword for the arithmetic growth. And here, for the geometric growth, it's when we said for arithmetic, it's adding the same amount over and over again. Here, it's multiplying the same number every time. That is for the geometric growth. There, they started with 1, and then they did a double in the second one, and another double in the third one. It became 4, 8, 16, 32. It went on like that. So here, doubling is the multiplying that same thing every time. That's the thing between these two things. And a simple, very simple example could be doubling of a magic bean. The size gets bigger and bigger, faster and faster. That's the key thing. A pair of rabbit is another example which we can look at. But what we have seen in the recent times is the COVID thing, which is in the next slide. So there, it is not quite easy for the human mind to really predict what's coming when the growth is actually exponentially increasing. We had this patient 0 in the COVID, and then probably he or she met 2-3 people, and those 2-3 people met another 2-3 people or a family or a gathering. And we could see that during the lockdown, there was a considerable break of spreading. But once that lockdown was released, and there was a huge increase, and the growth was unpredictable for many, many people. And it was not easy for us commoners to clearly predict what is coming and how much can it grow. And that is quite lingering even now. Yeah. And the next is, so in a sequence, like what is the next term in these sequences? Maybe you can start typing in the chat box. It's a very simple exercise. The first one, 6, 12, 18, 24. You'll get to know there is a difference, and then there's a sequence. What is the sequence for the next term in the sequence of 10 starting, and minus 30. And for the 10 starting, what is the sequence? And for the third one, like, what is the next term? And for the third one, 23, 23, 23, 23, that stays there. And what happened to the negative ones, like -4, moves on. So here, these things, like even if I ask the children, like they would look at it, they'll stare at these things and quickly come up with these answers, like as we all have been doing now. So finding the next term is, we all would have gone the same way, like what's there on the next one. It's, we look at the difference. And what is the difference which is common are in the sequences which we have seen? Which of these have common differences? Is it 1, 2, 3, 4, 5? Which of these have common differences? All of them, or? There's a common difference. The first one, yeah, of course, 6 is a common difference for the first one. What about 2? And what about 3? 23, 23, is that a common difference? Yeah, there is a slight confusion. 1, 4, and 5th are common differences, but second is obviously not, because it just, the difference is obviously different. But for the third one, there's no difference, but it's still common. So the common difference here is 0, which is common for all of them. So that's also a common difference, we can still say. And so that's it's not a, is it even an arithmetic progression? Not so sure, but it's quite easy to predict and know all these things because there is no increase or decrease in the third one. Yeah, moving on to the next one. So what is the 13th term? How do you find a 13th term in a sequence? In a sequence like this, what's the 13th term? In 5, 11, 17, 23, and 29, how do we find the 13th term? We can look at 5 as the first term. We can just look at 5. And first term is 5 is equal to 5. Just hold on there and don't need to put importance in 5 plus 0 times 6. We'll hold for that. And the second term is 11, which is 5 and an addition of 6. And for the third term, it is 17, which can be rearranged as, regrouped as 5 plus 6 plus 6. And for fourth term, it's 5 and 3 6s. And for fifth term, it's 5 and 4 6s. And in that case, for the 13th term, it will be 5 and 12 6s. And that's 72 plus 5. Yeah, most of you have got that. I've seen 77 as an answer there. So from this, the first column, we move on to the second column where we see 5 plus 0 times 6, 1 times 6. We find that, and it'll be nice with the children. You go about the sequences, let them start writing all the, maybe children want to write all the 13 terms in that sequence and then find the 13th term. That is absolutely fine. And it should be that way so that the question lives with them until, and it should be an exploration along with them to find the formula. So let's see how we find the nth term of such a sequence. And if in the same sequence, how do we find the nth term? We have found 13th term as 5 and 12 times the difference. For the nth term, it should be 5 plus n minus 1 times the difference. And once we know this, this becomes the formula which is written on the board in a corner, and it's just because it's also explored along with children. We haven't written the formula and then proved how it is working. Rather, we have some small examples and then lead them to the formula. And in the next one, so here we can also look at the first term as A1 or if the first term is 1, then we can keep it as 1. And if the first term is A1, then we'll just say A1 plus n minus 1 into D. And this is something which I've been doing in the class 4-5 itself. The next one, the sum of the sequence. The sum of the sequence is, I asked them, what is 1 plus 2 plus 3 plus 4? And many children say it's 10. And what is 1 plus 2 plus 3 plus 4 plus 5? It's 15. And when I ask the next one, it's again easier. But when I ask, what is the sum of the first 10 numbers and what is the sum of the first 100 numbers, children just go blank at that time. And slowly we can talk about this Carl Friedrich Gauss story, where how he actually found out this sum of the first 100 numbers very quickly in a flash, because it just played out in his mind. I'm not so sure if this story is true or not, but this is how it's going. But where he had seen the numbers at the end had been added together, 1 and 100, 2 and 99, 3 and 98, 4 and 97, and all of them. Or the other way is like all the numbers have been added from 1 to end and in the reverse order as well. And once that is added, you get the first number and the last number, the sum of the first and the last number, and that many times which was there in the terms. Like if there are 100 numbers, then it's 100 times 1 into 101, 1 plus 100. So it ends up as n into n plus 1. But the thing is here, because we have added it twice, so we have to make it half of it. So it ends up as n into n plus 1 by 2, which we can see in the next GIF. It's a very nice GIF which we can look at. So the same number is added twice, and because it's becoming as 2s, so now half of it becomes the sum of the numbers. And here also in the sum of the numbers, we can look at it as, because 1 is the first number, if we had replaced that with a1, it becomes as n times a1 plus an, which is the last term, divided by 2, half of it. So if we move on a little bit more to even look at those terms an also in the next slide. So there a1 stays a1, but an we have found out that it's a1 plus n minus 1 times d, which we have found in the first one for the nth term. And if you use that and then just deduce that whole thing, then it becomes like n into 2 times a1 plus n minus 1 times d by 2. So here we have also included the nth term, which we have written on the board in a corner along with children. So we use that here to also find this next formula, and these two formulas go on the board for a while. Now we have these things. We'll look at some of the other questions, how it can come. The next one. So here in this puzzle, start finding in the sequence what happens in the first figure. What are the numbers which are missing? Tell the numbers for the line where 21 is. What are the other 3 numbers? There's a number between 7 and 15. There's a middle number of that. And that number comes, wait. Is it doable? Yeah, that 11 is correct. And once you've got that 11, 3, 7, 11, 15, once you've got that 11, now you use that 11 for finding the 21. Nadia, we can put this in the group as well a little later. Yeah,
Yeah.
we can move on to the next puzzle.
Very nice puzzle. Yeah. Put
And in an arithmetic progression, the sum of the third and the 15th terms equals with the sum of 6th, 11th, and 13th terms. And how do we find these things? And especially one question is like, which term of the series must be 0 in such a case? So when in many cases, like when two terms are equal to the other two terms, it's obviously there is one negative number and positive number sort of a thing which is available. So which of the terms which is 0, which should be 0 is, so you find those third term and the 15th term on one side and the 6th, 11th, 12th, 13th on the other side. And we start finding, and eventually we get that it's the 12th term, which is 0 here. So, but finding it last week's algebra comes into handy this to solve these equations, and many times we have such questions, and all these questions are so interesting in the 10th curriculum board, where all these could be played more like a game. Then it's quite easier. Like the previous one, it didn't feel like we are going to use the formula, but here it feels like we are already using the formula. I'm going to use a plus 2d. Whereas in the previous picture, nobody would have done that. The intuition keeps working in that earlier one, but not in this one. Here but that's precisely why we need to wait for the formula to be explored along with children. The next. You can read this. An arithmetic progression has 23 terms. The sum of the middle 3 terms of this arithmetic progression is 720. And some of the last 3 terms of this arithmetic progression is 320. And what is the 18th term? Here, obviously, for the middle 3 terms, when we say that in the 23 terms, it's going to be 11, 12, and 13. In that, if you say the average would be the 12th term, similarly, the last 3 would be 21, 22, and 23, and the average would be 22nd term. And once we have found out that it's 240 and 440, then obviously the difference between 12th and the 22nd term is going to be 10 terms, and it will be 20 because of the 200 divided by 10. And once we have that 20, we know that 18th term is 6 away from the 12th term, and we use that and eventually find it. It'll obviously be nice if the steps were not given and you find the answer, which is a thing for the next slide. So there, let's take a minute to read, or maybe 2 minutes to read this thing and think about it. So for the 5th thief, there were no diamonds left. All the others, starting from the first, took half and one more, took half and one more. So what is it? And this question also can stay alive, and we can give the answer in the group. We can share this in the group as well. Yeah. Look at the next one. Yeah, those are the puzzles from my side, and Ramesh will take over from here. Thank you.
Yeah, thank you. Go back up. Yeah. No, that's fine, Nadia. Now so one of the things about geometric progression is it can be somewhat counterintuitive. The human brain is not very well wired to think of geometric progression. I'll give you this one small live example, which all of us can relate to during COVID time. It was March of 2020, and we were reading in the news the number of cases have gone up to now 200 and the number of cases had gone to 500. The number of cases next day had gone to 700 or some number like that. All these numbers were coming out in the newspaper. And I thought I'll sit down and start modeling it. I mean, as to how will we think about all these things and and start publishing the numbers. These publishing of numbers was just in my family group, but I used to very sincerely sit and do it every morning. Take all the numbers, different state numbers and deaths and mortality, this, that, everything. I used to publish all those numbers. And let's just say, I can't remember the number, but let's say I had predicted that at the end of the month, we will have something like 70,000 cases. And I can promise you at least some 20 people in various groups threw up saying, this is ridiculous. You're being pessimistic. This is your problem and all that. I said, it's just that geometric progression is very difficult to grapple with. And it's very difficult for a human mind to wrap its head around it. And with that in the background, I want to talk about 2 or 3 small geometric progression games. The first of them is, let's take a game where today is the 1st of January. Okay, Happy New Year. Today is the 1st of January. And what you have to do is you pay me 1 rupee. That's it. Okay. On the 2nd of January, you pay me 2 rupees. On the 3rd of January, you will pay me 4 rupees, double of the 2. On the 4th day, you pay me 8 rupees, which is double of the 4. Is the game clear? First day, you pay me 1. Second day, you pay me double of that, which is 2. The 3rd day, you pay me double of that, which is 4. The 4th day, you pay me double of that, which is 8. Okay. And for easy calculation, I can even tell you by the 15th day, you would have paid me roughly 33,000 rupees. Okay. Now, from my side, what I do is every day, I pay you 50,000 rupees. So first day you paid me 1 rupee and I pay you 50,000 rupees, which means you collect 49,999 rupees profit. Second day you pay me 2 rupees, I pay you 50,000. Third day you pay me 4 rupees, I pay you 50,000. Fourth day, I don't change what I pay. I continue to pay only 50,000 rupees to you every day. Okay. The question is, will you play this game with me? What does your intuition say? Pooja, you are the kind of friend I need, Pooja. I'll share my personal phone number and then we are going to play this game. Oh, Pooja said no. Okay. Why do you all say no? I thought Pooja said yes. Why do you say no, Pooja? Because I scared you enough with the COVID example, or you hate money? Lata, any reason why you won't play with me? Nadia, you can go down like 6 down. You can do 1, 2, 1, 2. Next one, and probably stop there for the moment. Well, on the 15th day, but you collected a lot of money, Pooja, yeah? How much? I mean, on the 5th, the sum total of all of them, we are talking about 33,000 rupees. So by the 15th day, you're paying me maybe 16,000 rupees. I'm still paying you 50,000.
1,000 rupees, sir.
But you still, but you collected a lot of money.
The doubling of the number later.
If you are
Sorry.
stopping this game by 16th or 17th day, I am ready to play.
Okay.
No, actually, the month is 31 days over here. And exactly on the 15th day, it is 33,000. So if it's 16th day, it will be 66,000. But when you see the difference here, 50,000 and 66,000, 19,000 is the first profit you're getting immediately. And then it goes on the profit here after 16th. It's, enormous in comparison to what I get the first 15 days.
Good. So Lata, try this out with some of your family members or in your classroom and see how many people who, without providing the scare of the COVID example I took earlier, or without much knowledge of geometric progression, try it out. Of course, you won't play this game. You should not. As a math teacher, all of you are right in terms of Pooja, Lata, everybody not wanting to play this game. Simply for the fact that when we come to the 31st day, the 31st of January, you will pretty much be paying me 2 to the power of 30, which is approximately a billion rupees. Okay, 100 crore rupees is what you have to pay me on that particular day. So this is one example. This is not so much a puzzle, but you can play it like a game and ask this question without scaring the class away with the COVID example I gave, but just to say, why don't we play this game? And this is the game, and I will pay you so much. And how many people will put up their hand? Chances are, if there are 15 kids in a class, all the 15 will put up their hand. Okay, this is one thing for us to understand for geometric progression is it grows in a way which is very, it's not at all intuitive, and therefore definitely requires a certain amount of modeling, certain amount of rigorous mathematics for us to be able to see what it is. Okay, yeah, we can move to the next slide, Nadia. Okay, the second one I wanted to kind of talk about very briefly is what is called Zeno's paradox. Okay, so there is this person, philosopher, mathematician. At that time, thankfully, they didn't break all the subjects into maths, physics, chemistry, and biology. So all people were quite happy to think about all kinds of problems. So Zeno's paradox is like this. He wants to walk 1 kilometer. In the first 5 minutes, he walks half the distance, which is 500 meters. In the next 5 minutes, he walks half of that, which is 250 meters. Next 5 minutes, he walks half of that, which is 125 meters. The question is, when will he reach the destination? After how many minutes will he or you reach the destination? You can type it out in the chat box if you like. Anybody? Okay, we'll post it in the group. Think about it and let us know when will you reach the destination. Will you reach after 40 minutes, 100 minutes, 200 minutes, 500 minutes? When will you reach the destination? Okay. And in the interest of time, I will go through the next 2 slides somewhat quickly. We talk about compound interest, right? The compound interest formula, which we all use, is A equal to P into 1 plus R to the power N or T or whatever it is, right? N being the number of years. This is the calculation which we use for calculating compound interest. Now, if we were to compound it every 6 months, then we use the next type of formula where A equal to P into R by 2 to the power 2 to the power of T. To the power of 2T. And if you were to compound it 4 times, it will be A equal to P into 1 plus R by 4 to the power 4T. This is clear. The question is this. If we have to compound it instantaneously, which means you're compounding it every nanosecond, what does the equation become? Okay. Now this equation very interestingly becomes something else. This equation becomes the amount will be equal to the principal times e to the power RT. Yeah, you can go down one more also, Nadia. Okay, so the thing becomes the total amount becomes the principal into e power RT. And we have seen e before. And this e, which is, we are doing compounding of an interest, which is a social phenomenon. And this e, which is a very physical phenomenon, kind of enters here, where the amount becomes p into e power RT. And this is something which is very, very widely used in financial price modeling, where when price series follow a certain distribution, when you're analyzing stock markets, when you're analyzing option pricing, and all kinds of financial instruments, when we have to model the log of P1 by P0, which is essentially, if you take the log on both sides, it will become log of A equal to P plus log of e to the power RT. And you can rearrange the terms and it will show you that the price series, if you think of it in terms of price returns, it follows a normal distribution. Which then brings me to the last slide for me before I hand it over to, yeah. Okay, you can show the whole slide itself. Okay. Here there is another interesting thing where if anybody had a stock portfolio of 5 lakhs, banks will usually lend using that as a collateral. That means your 5 lakh stock portfolio has been surrendered to the bank and they will lend you 75% of it. Okay, so let's use a case where it is 1 lakh. What happens is the bank will lend on 1 lakh. You can buy stocks worth 1 lakh and then you can pledge it to a bank, which will now pay you against the pledge 75% of it, which is 75,000. And with that, you can buy stocks worth 75,000, which you can pledge to a bank, which will now be able to give you 75% of the 75%, which is nothing but 0.75 squared. And then you can take that and pledge it to a bank, which will now give you 0.75% of that. And that basically creates a leverage of, if you had 1 rupee or 1 lakh of rupees, you could buy, using this kind of financial leverage, stocks worth 4 lakhs. Which means that if your portfolio goes wrong by 3% or 4%, you will be out of pocket to the extent of the 4% times 4, which is your leverage, equal to 16%. And this is one more beautiful example on geometric progression, which led to the global financial crisis in 2008. Now, all these examples, whether it is Zeno's paradox, or whether it is that 1 rupee, 2 rupees, 4 rupees, 8 rupees, and I paying you 50,000 rupees, or this borrowing capital, all of these are illustrations to really drive home the point that geometric progression, whenever it comes or we come across it in life, it is better that we don't trust our instinct and rather we use a more rigorous price modeling and financial modeling or mathematical modeling rather than using our instincts. And because it is not instinctive, it is not intuitive, because simply the human mind is not wired to think geometric progression. It's a limitation of our mind itself. Yeah. So with that, I conclude and I will move. Bama, all yours.
Yeah, thank you, Ramesh. Actually, you could have, I think my part won't take that long, so you could have done it.
No, that's okay, because I also have to kind of leave a little bit early. So that's
okay. Yeah. Okay. So, yeah, next, please, Nadia. So, in this, I would like to just briefly tell a few interesting activities that we can do with calendars, and this is to supplement, classroom teaching. And these activities can be done in across many
Please,
grades.
can you be a little louder?
Yeah. Yeah, 1 minute. Is this better? Okay, so I would like to, these activities of the calendar, they can supplement classroom teaching. And this can be done across many grades, starting from, even simple addition and average and sum from maybe 5th standard on to algebra, activities with algebra in 7th and 8th grades, and many small puzzles too. So let's now look at a few. So if we look closely at a calendar for any month, right, if we know which day of the week the first of the month is, then pretty much we know the days of all other dates in the month. So because if first is a Friday, then 8th, 15th, 22nd, 29th are all Fridays, like in October, what we can see. And for November, if, for example, they are all Mondays, because the first of the month of November month falls on a Monday. And they're all like one below the other in the calendar. And so like this, for any month, if we know the first date of the month, we know all other, all other days, the particular date is going to fall on. And that's of course because there are 7 days a week, right? And the calendar dates and days, they are all based on what we call as modulo 7. That is, you divide by 7, the remaining, and so it's all based on the seven tables, as you can see. Yeah, 7 times tables. Next, please. So Senthil just now talked about many arithmetic progressions, and in a calendar you find many of them. Like for example, every row in a calendar month is an arithmetic progression. The common difference is 1. The green line, for example, or every column. If you look at the yellow line, it's the common difference is 7, and every diagonal, like shown by the red, is the common difference is 8. And also, if we move like a horse on a chessboard, say, like dates 3, then 12, then 21, then 30, then this also forms an arithmetic progression. And we don't have to use a term arithmetic progression. We, even for class 6, we can ask them to find the different patterns, and we can ask them like, what is the rule followed? So the rule is always +8 or +7 or +1 or minus something. And so this can be done as a simple activity for even lower grades, just finding patterns. Next, please. So now if we ask the children, what is the sum of any row, right? And after you do so, you ask them to think and see, is there an easier method to find the sum of any row? So next, yeah. So suppose you look at any row that has 7 dates, right? The one marked in red, say, okay, the red row. And in this, here, the middle number, right, is the average. So you can ask them to try. So find the sum of these numbers, like 17 plus 18 plus whatever, till 23. And if you divide by 7, what do we get? We get the middle number, that is 20, right? So what is the sum of all the 7 numbers? Is nothing but the middle number of that row multiplied by 7. And similarly, in any row, right, the sum of the first and the 7th number. So for here it is like 17 plus 23, right? It's the same as 18 plus 22. And that is like 40, and that is twice the middle number. So like this, there are many, 19 plus 21 is again 40, which is twice the middle number. Now take any column. If there are 5 numbers in that column, once again, the middle number gives you the average. So the one marked in purple, like 1, 8, 15, 22, and 29, the sum, you can do the sum by just multiplying 15, the middle number, and that will be the average, times 5. And so this is when a row or a column has an odd number of numbers, and that's the middle number. So what happens if it has an even number of numbers? For example, the Monday column, it has only 4 numbers marked in light blue, 4, 11, 18, and 25. So what happens then? So now the average is nothing but the sum of the middle 2 numbers like 11 and 18 and then divided by 2. Right? That will be the average of all these 4 numbers. And that multiplied by 4, that average multiplied by 4 gives you the sum of the 4 numbers in that column. So now, what is the average of all the dates in October? Suppose there are 31 days, right? What is the average? Can anyone tell me? Can you type it out, please? So take all the numbers in October. If you want to find the average of all the dates, without too much, calculations.
16.
Huh?
16.
Yes, 16. That again is the middle number. Yes, thank you. So the middle number will form the average because, and what is the sum of all these numbers? That middle number times 31 will be the sum of all these numbers. And so this is very similar to the Gauss's story that Sendil told us about. Next, please, Nadia. So now if we look at, right, a 2 by 2 square in the calendar, right? So suppose we consider 3, 4, 10, and 11 as shown. Yeah. So if you look at the sum of the diagonals, 3 plus 11, that will be the same as 4 plus 10, and that will be 14. Similarly, if you look at any 3 by 3 square, what do we get? We get the sum. What is the, if you add all these 3 by 3 numbers, what is the numbers? Once again, what is the sum of this 3 by 3 square? That is 12, or shown in red. The sum will be the middle number times 9. And the middle number, once again, will be the average, right? So, yeah, Suvarna, yeah. So that middle number will be the average. So the average here in the red square, 3 by 3 square, will be 20. And the sum of all these numbers is 20 times 9. And similarly, in this 3 by 3 square, you can also find other patterns like the if you add 12 plus 28 is nothing but 14, the two diagonal, the corner numbers like 14 and 26. Right? And that will be equal to the sum of 13 plus 27 and the 19 plus 21 and so on. And that again is the center number times 2, 20 times 2, that is 40. And again, if you cross multiply the set of the 4 numbers, this is another one. So if you take again the 2 by 2 square and you cross multiply like 3 times 11 and 4 times 10, and you take any kind, this kind of any, 2 by 2 square anywhere, any place, the difference is always 7. Like 3 times 11 is 33, 4 times 10 is 40, and the difference is 7. And can you prove that this is always 7? And we can use algebra to prove this. How? That's what I've given on the left. So any place, okay, any number you start with, the corner of that 2 by 2 square, suppose you mark it as x, the next 11 will be like x plus 8, right? You're taking a square. So if x into x plus 8 minus x plus 1 will be your next number times x plus 7. So now you solve for, what do we get? The x cancels out, and then we get always 7 as the answer. So this proof by algebra, where x can be any point in the calendar, the starting of that square anywhere in the calendar. And then, so this holds for all 2 by 2 squares. So like this, if you want to prove something, across the calendar for any number, any what you take, we use algebra in this. Next, please. So similarly, suppose we take a 2 by 2 grid sum, right? So can you, so now here, suppose we have, if you're given that sum of that grid, okay, you're given that 2 by 2 grid sum, can you find out which one it is, which 2 by 2 square it is? So for example, if you're given the sum of all the 4 numbers, in some 2 by 2 grid is 28. Can you find and can you mark that grid, that 4 by 2 by 2 square in the calendar? So once again, you use algebra. So you say x plus 1, and then x plus 7 plus x plus 8 should be 28. And if you solve for this, you get the value of x. So you know which 2 by 2. So this is another nice thing. And suppose it's a 3 by 3 grid, and you're given the sum of all these numbers is 180. And again, can you find this grid? So again, if you use algebra, we can find the value of x. And by this, we can, if we can use a center number also as x. So it can reduce, if you use a center number of x, the number of algebraic calculations you need to do also reduces. So the center number is x, the number above it is x minus 7, across the left of it is x minus 1, right of it is x plus 1. So all these plus 1s and minus 1s and plus 7, all these cancels out. So you get it is easy to solve. Similarly, if you're given a column, say sum of all 5 numbers in a column is 75, then can you find which column it is, right? It's a 5-number column that you're given. So is it Friday or Saturday? And again, you can find. So here is another puzzle which you can create for the children, shown on the bottom left, right? So suppose you're given some random rectangular grid that is part of a calendar month. That's all you told the children. And over here, you fill up only one date, say 12, right? Only 12 is filled up. So can you fill the rest up? Can you find the sum and things like that in the shortest possible way? So we know the center number, and we can fill up the rest of the numbers as shown, because they all follow the arithmetic progression. And again, we can use algebra to solve, or in an easier way you can solve. So there are a number of such small puzzles which you can create and give the kids. Next, please. So another nice activity which the children enjoy is you ask them to make their own calendar month. So we see that in any month, right? We have maybe like this month as shown, we have 5 Mondays and we have 5 Tuesdays. But the rest of the days, like Wednesday, Thursday, Friday, Saturday, and Sunday, they appear only 4 times, right? You have 4 Saturdays, 4 Sundays in this particular month. So you ask them on simple puzzle. Say that you like Monday's calendar very much in your school. You like your school timetable very much. There are 2 games periods. So you like Monday very much. And then so you want the maximum number of Mondays. Yeah, before that you ask them, like these days, what is the maximum number of times they can appear in a month? So if it is a 31-day month, 3 days will appear 5 times, right? And if it is a 30-day month, only 2 days can appear 5 times. And if it is a 28-day month, like maybe, only none of the days will appear 5 times. All of them will appear 4 times. So if you want to have, if you want that month to have the maximum number of Mondays, okay. So where should that month start? Should it start on a Monday or a Tuesday or a Wednesday or a Thursday? Right? So it can start, of course, it can start on a Monday or a Tuesday. So let the child figure it out. And so the first day of the month should start on a Monday or a Tuesday, right? Suppose I don't like Mondays. So can you fill in the days in such a way that we have only 3 Mondays? Is that possible? Or is like if a month, what is the maximum number of days a month can have if it has to have only 3 Mondays? Right? Or some questions like that. What is the maximum number of, what is the minimum number of days a month should have if each day has to appear at least 4 times, and things like that. If it's a 30-day month, how many days, how many days that can occur 5 times, and so on. And then we have a puzzle like, say today is a Saturday. So this is a different kind of a puzzle you can ask. So today is a Saturday. So a man tells you that he will meet you after 40 days. What day will that be? And, does the answer depend on the number of days in that month? Can it have 30 days, 31 days? Or does it depend on that, or is it independent of that? And so on. So these type of puzzles are really, they are quite common, and they are found in many of these entrance tests like bank exams and so on. And there's a particular methodology to solve them, right? Once you know, then it's straightforward. So given any date, like say maybe 12th October 1965, or 1002 year, whatever year it is, it can be any year. What day of the week is it? Okay, is it a Monday or a Tuesday? So these kind of puzzles are asked quite often. So there are some very specific rules to solve these problems, and they all involve a certain amount of calculations. So some of the rules are like this, like a leap year. So every year that is divisible by 4 is a leap year if it is not a century. A century like 2000 or 1900, they have different rules. So for a century, every 4th century is a leap year, and no other century is a leap year in between. And a leap year is something that has 366 days, as we know. So for example, so 1948, 2004, 1676, they're all leap years because they're all divisible by 4. And also the centuries like 400, 800, 1200, 1600, 2000, they're all leap years. And none of the years like 2001, 2, 3, or 1800 even, or 1900 are leap years, right? So if we need to know, and if we have this in mind, we know the number of days in the year. So then we find something called odd days. So in a given period, like the number of days more than a complete week is called odd day. So for example, to find the number of odd days, you just have to divide by 7, and the remainder is called the number of odd days. So January has 31 days, so it has 3 odd days. April has 2 odd days, and so on. And an ordinary year, like 365 days, it's like 52 weeks plus 1 day. So an ordinary year has 1 odd day, whereas a leap year has got 2 odd days. So with this, we determine the day of the week. It is just a tedious process using these rules. And so there are some other, like, many other kinds of puzzles are these critical thinking puzzles, which we find. So these are like something like 3 days ago, yesterday was the day before Sunday. So what day will it be tomorrow? And things like that. It's just the wording and the English, and you just have to solve it. Yeah. So the idea is that you make it instead of the routine problems for children, like routine addition or average or finding a pattern and things like that. These kind of problems, if we give the children in between, it makes the class more interesting, and they start and let them think about it, let them spend time to puzzle. Maybe the next day we can solve it or something like that. Yeah. Thank you. Yeah, have any of you used these kind of puzzles in class? I mean, use the calendar to in the class.
We have used in our class for grade 4 children actually explore this calendar.
Oh, that is so nice. Others are such questions, or do you have any more other kind of questions in the calendar that you ask them?
Oh yeah, similar kind of questions and a bit more, some more questions added on to that.
Okay, okay,
The
nice.
children come up with their own magic squares
Huh.
using the calendar.
Yeah, yeah, correct. Yes, that is a nice. Yes, magic squares can be done. Yes.
Ma'am, especially when we do these days, right?
Yeah.
Sunday is 0 or 1. Sunday value, generally we assign some values like if Sunday is 0,
Huh.
right? Or it's 1.
So it depends on you, right? So if the rules followed. So if you're going to use Sunday as 0, then accordingly you have to subtract that many odd days, or get that many. So these are the procedures. So
But the rule can be changed, modified according to the questions then.
yeah. You can definitely come up with your own rule to solve these problems.
So when we solve from Shakuntala book, right? Mental ability question,
Yeah, so
right?
she follows a certain methodology.
Generally, she illustrates some basic rules, especially with the calendar and the dates when we work with it. Right?
Okay. Yeah.
And these students around grade 8 and all, they would have crossed with this Shakuntala books is a common handbook for them to go with that particular time. When we ask, they come with it. Therefore, my doubt is the rules changes from book to book then.
Yes. It changes from book to book, definitely.
Okay, thank you.
It's just a procedure that if you make Sunday the first day. So here Dhanashri is asking which day is considered the first day of the week. It depends on you. Like you want to consider Monday as first day, that's fine. But you base the rest of your
few students related to their pre-primary where the teacher would have taught Sunday, Monday, Tuesday. Sunday is the first day, sir.
Yeah.
Therefore, you have to assign the first value of that. 0.
Yeah, correct, exactly. Even I mean the same.
Because they come, because they will never forget, especially Sunday, Monday, Tuesday teachers, they will not forget, right? If we try to go with some other value, right? The question comes, either it is 0 or 1. They have some students, where we have faced it. When I try to give these puzzles, right? Sir, Sunday is 0. No, we have the argument among the students only. That's the only one.
Yeah, so if you can post one such puzzle where you had a confusion, right? We can look at it the next class. But as far as I know, you can use the rules will change accordingly. The way you calculate will change accordingly.
Okay, ma'am, fine. Nothing as such. The only one confusion what generally we have, Sunday is the first day or Monday is the first day. What value is to be assigned? That's all. Nothing else. Since it is flexible,
it doesn't matter really. It can be anything. Yeah.
Okay, ma'am, fine. Thank you.
Some Arabic countries have Friday as a holiday.
That's what we related. It's not we Indians. We take the first day as a leave. That is on Sunday. We'll take rest, then we will work it. Where those people start working and the last day they will take the leave. That is the difference.
Yeah, if we will start Monday as a first day, then Saturday, Sunday is a weekend, like that we can say. But if we will say Sunday as a first day, then where is the weekend? So
Yeah.
Ma'am, connection to this calendar, the lower grades like grade 2 and 3. In grade 3, we actually asked them to write down the date, birth date of their parents or somebody, and then they start framing the whole calendar of that year. Only with one single date, they make a calendar of that whole year. And
that's wonderful.
The grade 2 children and all, they get to do the previous month and the next month of any date given.
Yes,
So
very
it
nice.
gradually we move from one level to another level, and then we start finding on the patterns. From grade 3 only, they start exploring the patterns.
Very nice, very nice. Yeah,
Thank you.
nice, nice. Yeah. Okay. Thank you. Thank you all. I think we are right on time, right on the dot, 6:30.
Yes.
Yeah.
And at the same time, I would request everyone to please log in on the link I've just shared on the here in chat, and I'll also share it in the group. We would really require and appreciate your feedback, as it will help us do better. So yeah.
Thank you all for joining. Bye.
Thank you so much.
Bye.
Happy weekend, everyone. Thank you, Bama. Thank you,
Thank you.
Sandesh. And
Thank you.
Thank you. Bye.
Hello,
Bye.
ma'am. Is Sendil sir here today?
Yeah, he's there, I think, no?
I think he just left a
Oh,
while
he
ago.
just left. Okay.
Thank you, ma'am.
Thank you.
Wonderful session.
Thank you. Bye.
Bye. Thank you, everyone.